Okay, so here's section 17.4, where we look at the Einstein relationship. So this relationship really relates the diffusion coefficient to the mobility, which are the two elements in the drift diffusion equation. So let's dive in. So here's this term we have looked at so far. We've looked at the drift term, where we've determined a mobility, we've calculated an electron density, we can measure an electron density, we can relate that to doping and scattering effects, okay? And of course you can do the same thing for holes as well. But now we're going to start looking at the diffusion term that is in this transport equation for electrons and for holes. So let's imagine you have a system that is driven out of equilibrium where somehow you have introduced a pile of charge in at a specific location, say at a semiconductor. So in thermal in a thermal environment where you have scattering, half of the charge will flow left and will flow right. Then the other, as you evolve in time or in space, some more charge will flow left and flow right. And eventually, the system will have diffused out. Basically, the charge has diffused away from the original spiky spot or pileup of charge. So this is sort of a temporal description, but we can also now look at a spatial description where we look at a diffusion flux. So let's assume that we have a gradient of charge between in our device. Somehow we have managed to have a charge distribution that is not homogeneous. Let's just start from that. And we're going to look at a slab, ultimately an infinitesimally small slab of this charge. Okay, and if we're assuming independent random motion, half of the electrons will move to the left and half will move to the right. And we could write down a current for that. In general, the electrons, on average, the net movement will move to the left. They will move against the gradient. So basically, they diffuse away from the higher electron density to even out the electron density distribution. Okay, so the opposite sign we would do for holes. We can write down an expression for the current as a function, again, of the thermal velocity in the system. And here we are assuming in a minute that the system is actually in local equilibrium. So we have been able to treat this semiconductor in a way that we introduce this gradient of charge, but still the system is in local equilibrium. That'll be a fundamental assumption that we'll do. So we'll divide the slab into a right-moving and a left-moving charge. So we do an integral over these ultimately infinitesimally small areas, and we have the charge and the velocity, and the one direction is negative of the other. Now, let's expand out. We can write this. We can approximate this by calculating the area here under the curve, which is the expression here, which is you take term here, and you move a delta x to the left and a delta x to the right. That gives you these two terms of differential area under the curve. And that means you can now, in a differential expression, describe a current that is flowing with a differential of the gradient of the charge, but you have a term that is now depending on the length of the slab that you're considering and the velocity, the thermal velocity that these particles make it through the structure. All right, we will define this coefficient as a diffusion coefficient. That's the length of the structure that we can imagine these electrons moving through and the thermal velocity that they move it through. Okay, and given that definition, we can define or relayed the current to a gradient in the carrier distribution. So in all of this, we've left out quantum mechanics in a sense, you might think, but it's really built in under the hood by calculating the available states in the system, which gives us a filling of the states, etc. So the assumption here is that under the hood, these quantum mechanical effects are built in, but there's also a lot of scattering in this structure. It's an interaction of many, many electrons in the system that balances out on the thermal, through thermal interactions in the system. Okay, so really these terms of drift and diffusion, they must be related to ultimately balance out to zero in local equilibrium, because we have a gradient of the charge like this, and that's causing a drift current, but at local equilibrium there can't be any current. So there must be a field that is associated with that. All right. So let's see what these relationships look like. So we have a term now here that we started out from. We have a drift term as induced by a gradient of charge. And we're going to try to relate this to the diffusion current, okay? So we're going to try to relate that to the mobility in the system. Okay, let's take a ratio between D and mu. And D we had just defined in the previous slide. We had the mu that we defined before. The length L that we considered was effectively the diffusion, the length that a thermal particle would move through the structure. And so we have a relaxation time that would slow the particle down, so it moves at a thermal velocity, gets kicked by some scattering event, and that would be the length this particle travels. So we can plug this in here, and we can expand this term out to have the kinetic energy like this. Okay? Now, if you ever took a course on statistical mechanics, this would be very familiar to you. Basically, per degree of freedom in a system, a particle would have 1/2 kT of energy, of thermal energy. So here we consider a one-dimensional system, so we associate 1/2 kT with this kinetic energy, and then D over mu turns out to be kT over Q. It's kind of an interesting expression that really relates the diffusion to the mobility. Now let's do a slightly different but fundamentally very similar derivation. This is done by a nice description here from Colorado University. And so we have this gradient here. We consider a root mean square velocity of these carriers, so a thermal velocity that goes, again, as I said in the previous slide, which is L over tau. So they travel a certain length, and then on average they scatter it in a certain time, and that's their thermal velocity. We again have this assignment of thermal energy of 1/2 kT, and we do basically a similar calculation, but carry it through it directly through differential expressions. Okay, so they move. These particles move at a mean-free path. They scatter. We do the same assumption that there is a net flux to the left, down the gradients. In this case, to the right. And we calculate these fluxes now. So there's a left-to-right flux that is just defined like this in this form, and we have the other distribution that travels to the right. So, and we have a net flux in this form. Okay. Now we are basically pursuing the same type of derivation here. We have a net flux left and right. Take the difference, we have which gives us then the net flux, And we can write this down in terms of the differential of the infinitesimal slice that we really considered. Here is our term like this. The negative sign is that we're going down the gradient. And we have an expression now for the electron flux, or for the whole flux. It's really the opposite, just different sign for the charge. And we have lumped together the second and third terms in form of a diffusion constant that we can do here. So again, diffusion constant is really the length that the holes might travel, and the thermal velocity, or for the electrons, it's just same term. And we have the definition of current density as induced by a gradient of charge, either holes or electrons. So this is very, very similar to the derivation I had just shown. In a sense, it's somewhat of a repeat with slightly different notation. Again, we're assigning the equipartition theorem, where it states that for each degree of freedom, we give it half kT. And we set the kinetic energy to the thermal energy. Here you can just add the factor of 1/2 to it in a one-dimensional system. And this means this must be true in equilibrium. So this relationship that we're going to derive, again, holds in equilibrium. And we come to the same expression as what we had before, that d over mu must be kT over q. So diffusion coefficient and mobility must be related, and this is the Einstein relationship, like this. And this is both true for individual diffusion coefficients for electrons and their mobility, and whole diffusion coefficient and whole mobility. Okay. So again, diffusion and mobility must be related. So there's another way of looking at this and deriving it yet in another way that is somewhat shorter, but you have to have a little bit of device insight already here. All right, so let's start out again from the drift diffusion expression that we had written down at the beginning of the class. We have a drift term here that depends on electric field, and it has the mobility in it. And we have a gradient of the charge that has the diffusion component in it. At equilibrium, these terms must be 0. Okay? That means we can balance out the equation like this, and we can have an expression here where this is dn dx divided by n. You can integrate that function over a certain distance. Okay? So consider a gradient of a charge density, and that must relate to the electric field. Similar to what we had done in the past, where you look at a charge distribution in the system, and you integrate that charge over space, as in here. You can have an expression that means if you have a charge gradient, you must have built in a potential in your structure. Okay, so this gives you now a ratio of N2 over N1. Given if you have any sort of gradient between charge level N1 and charge level N2, there must be a voltage that is dropping off in between here. Okay? Now, we can get to this ratio in this structure in a slightly different way. If we had this p-n junction like this, and let's not worry about exactly how we put these together, but we know that if we had a p-type conductor here, an n-type conductor here, we could draw a p-n junction like this, and we'll go into more details like this. But I could calculate an electron density given that I have a conduction band edge and a Fermi level. And I can do that the same way on the right. And I know that across this device, the Fermi level must be constant. Okay, that's local thermal equilibrium. And if I take the ratio between these, N1 and N2, I find that there must be a difference between EC1 and EC2. And that is the built-in potential of this p-n junction. Now, if I set these two ratios that I have computed here and here to be the same expressions, and take the log, I find, again, the Einstein relationship, like this, in local equilibrium. Okay, so here we go. This is similar, if you will, to what we have discussed in terms of capture and emission coefficients and the Shockley-Reed-Hall discussions. Okay, again, one process counterbalancing the other. Same here. Diffusion must be related to mobility in some form, and the Einstein relationship at equilibrium is the one that relates those two terms. Okay, with that, this closes out the section. You can read up more in the textbook. And drift diffusion and recombination are these elemental processes that we have in device physics, and the mobility can be measured, carrier concentration can be measured. These characterize semiconductor devices. And these characteristics will flow into our understanding of electron flow. We can build simulators where we can design these structures, or we can have analytical expressions where we calculate current flow as well. And that's going to be the topic of the next segments. So I'll see you there. Thank you.